right, so ladies and gentlemen, we're going to take a look at linear programming. This is lesson 3.4. And no, it will have nothing to do with computers or writing code, even though that is a pretty useful skill to have nowadays. What we're going to do are find the maximums and minimums for what's called a given region. So we created these regions in lesson 3.3 when we intersected these inequalities. So created a shaded region. And so what we're going to now find is what's the largest possible value, what's the smallest. So when we say regions, we're going to talk about shaded regions. Now, why would we want to find maximum and minimums? Because we want to optimize. This is what we're actually doing, is optimizing. So we're finding the maximum or minimum values of some quantity. Well, this is really what real world math looks like. We're going to be going through and finding what's the maximum profit I can have for something. What's the minimum cost I can have for producing something? Now, there probably aren't many business owners that are sitting around and doing the mathematics that we're doing, but what there are is there's some pretty rich computer programmers, some pretty rich mathematicians who are creating the programs, creating the code, doing the mathematics that optimizes things for these business owners. And so that's really what we're looking to do, is to maximize or minimize our features. And that's a part of life. The objective function, that's what you want to minimize or maximize. All right, so there are times that we want to, objective functions that we want to minimize, like the cost to produce something, the number of hours that we have people working, because that's cost out of our pocket as a business owner. I'm going to minimize the number of papers I collect. There are things we want to maximize. We want to maximize cost, or I'm sorry, maximize profit. I want to maximize productivity. I want to maximize your grade. And so anytime we can relate something to an equation, there are certain ones we want to minimize or maximize. And then constraints are the system of linear inequalities. So this is what we did in lesson 3.3, that determine what we call the feasible region. This is your shaded region that we are going to work with. All right? So let's take a look at what these problems look like. So we need to find the maximum and minimum value. So that means this is our objective function. All right. So this is a cost, more than likely. And so our cost is equal to 2y plus 3x. And so what we're going to do is we're going to find the minimum cost, which is good. We're also going to find the maximum cost. We're going to find out where that maximum cost is so that we avoid that, so that we know at what point am I actually getting close to the maximum cost. And then here are our constraints. We have to have x is less than or equal to 2. And so they actually, in the problems you're first going to look at, have graphed those lines. This is x is less than or equal to 2, the solid line and shaded to the left. We then have y is greater than or equal to negative 1. So here's our negative 1. And we're greater than or equal to negative 1, so that's why we're shaded above. And then they graph this line. And so if we solve that, we have y is less than or equal to x plus 3. And so we can see the y-intercept of 3, and we can see that we're going up 1 over 1 for the slope. And then here is that line. So this is y is, and we've gone less than, so we have y is less than or equal to x plus 3. And so this is the shaded region that we have. Well, that's a whole lot of ordered pairs, a whole lot of x and y's. Well, the cool thing about linear programming is these maximum and minimums are only found at intersections. So when it says find the maximum and minimums, you're actually looking for where things intersect. Those are the only things we're going to focus on. So we're no longer going to have this plethora of ordered pairs to check. We're only going to have 3. We have 3 constraints, so we have 3 ordered pairs to test. So I've got to actually go through and identify where those intersections are, where green and blue meet, where red and blue meet, and where green and blue meet. You do have to name those ordered pairs. That's what we've done before when we've tested. You have to have a value to plug in for x. You have to have a value to plug in for y. So in this case, this is the ordered pair 2. And be careful, guys. This is your x-axis. So 1, 2, 3, 4, 5. So this is the ordered pair 2, 5. That's going to be one of the values that we test. This is going to be the ordered pair 2, negative 1. And then over here, this is your origin. So negative 1, negative 2, negative 3, negative 4. And then down negative 1. So we're just testing those three ordered pairs. So this is how I end up testing. This is what my work looks like. These are my possible ordered pairs. So these are my xy's. This is my function. And then this is the output. This is my cost. Or my C. I guess I don't know for certain that it's cost. So I'm going to put these ordered pairs into my table. And then we're going to go through and evaluate those. All right? So when I take and plug those in, I'm plugging them into our objective function. So I have 2 times 5 plus 3 times 2. Notice here x and y are switched around. So the y is getting plugged in first, x is getting plugged in second. 10 plus 6, you can do mental math or on your calculator, we get 16. I don't know whether that's the maximum or minimum, so I keep going. I do 2, negative 1. It's going to be 2 times negative 1. Remember, it's 2 times y plus 3 times x, so 3 times 2. Negative 2 plus 6 is 5. Once again, we now know that 16 could possibly be our maximum. So we could have a maximum at 2, 5. We don't know whether 5 is our minimum or not, so we have to plug in that third ordered pair. So 2 times negative 1 plus 3 times negative 4. This is negative 2 plus negative 12 is negative 14. So what you found is your maximum and your minimum. So this is our max, and this is our min. And so I'm kind of running out of room, but we need to find those. So how do we write our answers? We're going to write it as a minimum of negative 14 at negative 4 and negative 1. I need all of the information. I need to know which one's my minimum. I need to know what that minimum is, and I need to know where to find it. I then have a maximum of 16, so I'm getting these numbers from the table, at 2, 5. Now look at your graph, ladies and gentlemen. If we take a look at our graph, let's see, I can get the highlighter pen. Here's where 2, 5 is. That's my maximum. Here's where negative 4, negative 1 is. That's my minimum. It really does kind of fit with what the graph shows us. The maximum was the highest point. The minimum was really our lowest point because they had the smallest x and smallest y. Not always going to work that way, ladies and gentlemen. It really depends on what that objective function was. But here, visually, it does make sense. So here's what you guys are going to do. You're going to open your book, so you don't need graph paper for this one. But I've cut out the graph there for us to go over tomorrow. So you are going to open up to page 166, and you're going to do number 11. And so what you should have is a table of values. So I should see your table. I should see your x, y. I should see your function. And I should see whatever you're maximizing. And in this case, it's C. So I should see your C. So I should see those. And then I should see a max of blank at blank, a min of blank at blank. So that's the work I should see for number 11. Don't put it on your notes, guys. Put it on your homework because that's where it belongs. All right. Yes, what we're going to do, we're actually going to graph one of these. We're going to find the maximum and minimum of C equals x plus y. So this is my objective function. I save this for the end. This is where I make my table. All right, and the constraints are what we're going to graph. So good thing we did lesson 3.3 first. So we're going to graph x is less than or equal to 6. So 1, 2, 3, 4, 5, 6. I've got this vertical line, and this is why shading with the arrows is really nice. We're just going to draw in those arrows because with 4 functions, 4 constraints to graph, that's a lot of shading to have on here. But if I can start to see where things are getting narrowed down at, that's really going to help. I now have 0 is greater than, so I'll underline these in my colors. 0 is greater than, or x is greater than or equal to 0, so that's a vertical line through 0, so it's just right there on the axes. And it says I'm going greater than, so we're now in the middle. So I can kind of see where things are going to look at. So we're focused in on this region in between the two lines. I now need to graph y is greater than or equal to negative 2x plus 9. Solving for y to graph is really nice. So I'm going to start at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm going to go down 2 over 1. Remember, I'm looking for intersections. So I have an intersection right here. I've got an intersection right there of my blue and red. I need to keep these points going until I intersect down 2 over 1, until I intersect blue and green. So there's another intersection. So things look good there. All right? There's 4 lines. Remember, we need 4 intersections, so we're halfway there. I'm going to draw on my line. But you need to shade. It says y is greater than, so my shading should increase over this, should be going up. And last but not least, so this was the line we graphed in blue, and then we're going to graph in black. We're going to add x, so 3y is greater than or equal to x plus 6, and then divide by 3. We get y is greater than or equal to 1/3 x plus 2. All right? So we're going to start at 2, 1, 2, and then we're going to go up 1 over 3, up 1 over 3. And we can stop there because we're within those boundaries. We know nothing's over here on the right-hand side. So I'm going to hit those and connect them. And now I need to decide whether I'm shading up or shading down. It says y is greater than. So we're going to end up shading up. And so what happens here is we end up with 4 intersection points. Let's highlight those. We have an intersection point. We have an intersection point here. But we need to take it where we're looking at. Because the only place where I see red, blue, black, and green arrows is right here. And so this is my shaded region. Well, this is what we call an unbound region. All right? So we're not going to have 4 ordered pairs to check. We are only going to have 3. This ordered pair down here, we don't end up using because it didn't end up in that shaded region, in that feasible region. So I'm only going to have 3 of them to test. I need to name those ordered pairs, so I'm going to start from left and work to right. This is the ordered pair 0, 9. This is the ordered pair 3, 3. And then this is the ordered pair 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So we have 6, 4. Our function is 3x plus y. So we have 3 times 0 plus 9 is just 9. And so this is our cost. We have 3 times 3 plus 3 is 9 plus 3 is 12. And then we're plugging 6 in for x. So 3 times 6 plus y, so plus 4. 18 plus 4 is 22. All right? Now this one's a little bit different than what we've seen before. Because this is unbound, ladies and gentlemen, this red region is going to keep reaching up and up and up. It's going to keep going, going, going. Because it's unbound, it never stops. And so that means that this one has no maximum. It's never going to reach its maximum. If this is our profit, this is awesome because our profit is never going to stop. If it's our cost, this is a little dangerous, so we really have to watch it. But what we can do is we can pick a minimum. So we're going to have a minimum of 9 at, and then we name the ordered pair 0, 9. All right? You're going to do tonight for me as your second on your own. You're going to do page 166 on the graph paper. Number 12. Have a good evening, ladies and gentlemen.